Hey folks, this is a presentation that I'd like to offer because I have seen a lot of new people run into various different foils when they're starting to dig into MetaSounds. So just as a quick recap, and I want to keep this very quick. My name is Dan Reynolds. I am a technical audio designer at Epic Games. I have a lot of experience with MetaSounds because I work with the team that actually develops MetaSounds. So this guide is for brand new people, and I'm going to try to keep it as quick and as concise as possible. I'm not actually going to be getting into MetaSounds, the actual graph. I'm just going to be talking about the concept behind it so that you understand MetaSounds concisely. Okay, so in this presentation, we'll be in two different parts. One will be sort of talking about MetaSounds and how it sits inside the larger audio engine ecosystem. And the second part is going to be talking about the graph itself, the nature of the graph, which is sometimes called a DAG, or a direct acyclical graph. So these are the different sections, and if I can, I'll try to figure out how to do the chapters in YouTube, but hopefully it'll be very quick. Okay, part one, the audio ecosystem. Okay, so you MetaSounds and everything else. MetaSounds are just one piece in a much larger suite of audio tools and systems. So I've seen a lot of people compare MetaSounds with various middleware, and usually the way that they compare it is a really poor way of comparing the two. MetaSounds are just the source render component of the Unreal Audio Engine, whereas middleware usually encompasses an entire suite of audio engine tools. So the appropriate comparison would be like however that middleware renders its individual sources. That would be the comparison to MetaSounds. And I don't think that it's a fair comparison because MetaSounds is way more advanced and capable than any of the other source renderers that I've seen. I think there are other people who see the need for MetaSound type graphs, and I've seen some development in that direction, but it's a very sort of bleeding edge area right now for game audio. It's not bleeding edge for regular audio. That's what's sort of interesting about this. You know, MetaSounds might be akin to, Reactor or Max MSP or Pure Data, but personally I find working in MetaSounds to be a lot more pleasurable. I actually find it much more like working in modular synths. That is to say, more specifically, that the Unreal Audio Engine has a huge suite of tools. Has a concurrency manager, has an entire spatialization and distance attenuation system, has a complete submix rendering graph for post-processing. All this, it's individual source effects. It has busing. It has 3D busing. There's so much that you can do with the Audio Engine tools alone to build out very cool audio experiences, and MetaSounds are just literally one tiny element of that entire full thing. And then on top of that, audio is integrated all over the engine. We have sequencer support. It's in you can spawn audio components in Niagara. So there's Niagara integration. And then obviously, like, blueprints, in our opinion, is a fundamental skill set for all Unreal developers, including audio developers. So, and you'll find that blueprints are, which are a much more traditional scripting system or programming system, visual programming language, allow for a very good balance. When you look at blueprints and MetaSounds together, when you combine them, you actually see this powerful synergy where blueprints can handle a lot of the more mundane scripting elements, and MetaSounds can do cool DSP stuff. So where that line is, where you decide to move that balancing line, is up to you in the project that you're working on. Because obviously MetaSounds has logic processing as well, but it's a little bit different. And as we get into it, I hope that you'll see how different MetaSounds are from something like blueprints. Okay. So let's just talk about the sort of execution pathway when we start a MetaSound, when we finish a MetaSound. And you'll notice OnPlay and OnFinished are these sort of trigger inputs and trigger outputs. And this all has to do with communication to and from the larger audio engine. So there are 3 threads of concern for audio developers. There's a game thread, there's an audio thread, or sometimes we call it the audio logic thread, and then there's the audio render thread. Furthermore, there are these things we call async tasks. And essentially, the game thread is where all your blueprints and scripting elements, all your gameplay sort of lives and passes through. Oftentimes, this is really important. Oftentimes, graphics will do things on the GPU and will fail to communicate state changes or information back to the game thread, and that is a cause of concern for audio designers and VFX designers also, but audio designers primarily, because we need that information oftentimes to come back through the game thread. So you have to think of the game thread as like the central hub of execution and information for Unreal. And the game thread has several synchronized threads. So, for example, the game thread and the audio thread are lockstep with each other. The game thread and the video update thread is locked together. So when your frame rate is 30 hertz, that means the game thread is updating 30 times per second. That also means that the audio thread is updating 30 times per second. When your frame rate is 122 hertz, that means the game thread is updating at 122 times per second. And that also means that the audio thread is updating at 122 times per second. So I want you to sort of think about that deeply in terms of timing and scenarios, around latency latency and all this sort of stuff. Now, on the game thread, when you call play sound or play MetaSound, it will first compile the MetaSound. Now, this may not always be the way that it works, but that's the way that it works right now. And that there's some very cool things that we can do to when we leave compilation to sort of happen as it's called. And one of those things is that in the future, it may be possible to procedurally create MetaSounds, which may blow your mind. But that would allow compilation on the fly essentially will allow us to do things like that. However, as an optimization, once a MetaSound has been compiled, its compilation data is cached, the graph is cached, and so that way, future calls maybe won't suffer from the delay imposed by compilation. Now, when it's done compiling, and if it's a small MetaSound, this will be an unnoticeable amount of time. But if it's a huge MetaSound, you could actually find some latency. So once it's compiled, the play command is sent over to the audio thread, and the audio thread then evaluates the candidacy of that sound. Remember, there's all these other things that can happen. We have distance attenuation, we have spatialization. The sound could be occluded, it could be too far away, it could be that the sound is unimportant, and maybe there's you have a max global sort of channel of voice count, and then you have a sound concurrency system which allows you to create voice groups essentially. And so it could be kicked out or rejected from any sort of voice group based on that information or priority or etc. But assuming that the sound succeeds and is a viable candidate for rendering, then we send a command over to the audio render thread and we generate a new sound source. And the new sound source is rendered as an asynchronous task into the audio render thread, right? And the audio render thread updates asynchronously from the game thread, so it's actually has its own update periodicity, and that update periodicity is defined by your platform project's buffer size. Now, you may be somewhat familiar with buffers and samples, and we will get further into what that means. But if, say for example, the default might be something like 1024 samples is the size of your buffer, right? And so that's the frequency at which the audio render thread is updating. It fills up, 1024 samples, or some multiplier of that, depending on how many channels are in your system. Maybe stereo, so it's gonna be twice as many samples, right? One for the left, 1024 for the left, 1024 for the right, etc. Sometimes we just call these frames, and that sort of lets us think of the sample rate as separate from the number of speaker channels that we actually render out. But yeah, so 1024 might be your sort of standard. You've seen 512, etc., etc., etc. And the way that you get this sort of render is that it will, unless the command from the audio thread comes at the very top and is ready to go at the beginning of a buffer, it'll end up just waiting for the next buffer. And there's a way around this that's using Quartz, but I won't get into Quartz. It's just another cool feature of the audio engine, which allows you to render in the middle of a buffer on the audio render thread. But basically it means that, generally stuff is going to update at the top of every buffer. The async task in our MetaSound, so every thread could be on its own sort of processor, but so can every async task. And so when you think about all of our sound sources on asynchronous tasks, there's a nice optimization there. It allows us to take up various nooks and crannies of our processor architecture without sort of being constrained by always being on the same core or whatever. So it allows us to spread the workload around very efficiently. And this is a really cool optimization. There are some downsides which I won't get into, but generally you just know that all sources are currently rendered on asynchronous tasks, and that includes MetaSound sources. This is not necessarily the same thing as sound cues. Sound cue graphs are evaluated on the audio thread. I don't want to talk too much about sound cues, but they're a very old-fashioned way of doing things, and they can actually stall the game thread. If you have too many very large sound cue graphs, you can actually slow the game thread down. Anyway, this is all to say, as we'll see, the actual update periodicity inside of a MetaSound, which also is rendering small buffers, is actually faster than even the default sort of audio render thread settings. So when the async task begins, when the rendering MetaSound begins rendering, the OnPlay trigger happens, and then it waits for either the audio thread to command the task to stop, or for the async task to indicate that it has completed. And so this is why it's really important that if your sound is meant to sort of manage itself, to end itself, and we'll talk about what that means in the next slide, you need to call OnFinished, because OnFinished will indicate when you trigger OnFinished, it will tell the rest of the audio engine, this sound is done rendering, and we will close out the async task, and that will make room for other sound sources. If you never call OnFinished and you never call stop from the game thread, then that voice will render forever. Okay, so that's something really important to consider. And then we have the audio thread communicating back via command structure that hey, game thread or gameplay or whatever, this sound is stopped. And that's very important if you're using, if you've got a delegate on the game thread that's like, hey, I'm waiting for this sound to stop before I start doing something else. Okay, moving on. So this is where we're talking about the one-shots, then the sustained sources, and the significance of audio components. Okay, so in the past, we used to distinguish sounds between looping or not, but looping is a really terrible word to use, because you can utilize loops in a sound that ends, that is intended to end. And so that's where we sort of flip it on its head and we say, is this a one-shot or not? And a one-shot sound is a sound that you can sort of play, fire and forget, and it will end itself. A sort of sustained source or a non-one-shot sound will probably require you to call stop. And that's where setting up the OnFinished is really important. But you can still have a sound that sustains and is considered a one-shot, but it's waiting for maybe some data from the game thread to call OnFinished, right? And that's okay as well. But it's important that if you have the one-shot interface implemented, that you absolutely do trigger OnFinished at some point, because otherwise the sound will persist forever. Now, this is where audio components come into play, and this is what's really important to understand about audio components. Audio components don't play sounds. Audio components are game thread remote controllers. It's the best way to think of it. It's a little control mechanism. It's a handle that you can use that allows you to interact with a sound across the thread boundaries, right? So the audio components on the game thread, and this is basically a handle on the game thread to control all sound sources that are playing. The one-to-one relationship between that audio component and a sound source that is rendering. And that includes MetaSound sources. So, things that are sort of, we've talked about, you may have experience in the past, pause, stop, volume, pitch. These are controls that you can do while the sound is playing via the audio component. And this also includes a parameter interface, which will allow you to feed data into the MetaSound. And this all goes through the audio component. So if you want to feed information or to change state inside of your MetaSound, you need to have an audio component to do it. Even if you just want to be able to play a sound and then stop it later, you need to have an audio component be in control of that sound. And so that's the idea behind an audio component. We want to replace the audio component with something that's lighter weight, maybe like a simple ID handle. But right now, the audio component is the only way to do that. Okay, so a MetaSound source that never triggers OnFinish will never stop rendering. I can't overemphasize this unless the user can command it to stop via an audio component, right? So you can have, infinitely sustaining MetaSounds, but responsibly, you need to have that associated with an audio component. So that's sort of need to be played through an audio component in order to stop it and control it later on. If you don't have an audio component, the sound will run infinitely. And usually what will happen is you'll get a warning or an error that kicks out. It's like, hey, this is an orphan sound or whatever, because it's not a one shot and there's no audio component. Okay, so this sort of brings us to interfaces. I sort of alluded to inputs and outputs, and we'll get into that a little bit. But the OnPlay, the OnFinished could be considered interfaces. The OnFinished is part of the source interface, OneShot interface. But there are other interfaces that you can feed in data and out, potentially out. This is something we want to add, is being able to feed data out of the MetaSound. So the interfaces are just a way to pipe data from some sort of external system into the MetaSound source. And that includes the source data, which is where the spatialization interface and the attenuation interface gets its information. And those are great things to take advantage of. Attenuation is basically gives you the distance the sound source is from the listener, and the spatialization gives you the azimuth and elevation angles from the listener. So you can do really cool things, based on how far the source is away from the player, essentially, and so on. So inputs, outputs, and variables. Basically, inputs allow designers to create custom data pipelines into the MetaSound source, which can be called via the audio components parameter interface. You can see here we're executing a trigger. I will get into this later, but triggers are considered data. And there's a custom trigger name. You can create, basically the in name is the name of the thing. And you can see the target is the audio parameter controller interface, but it's targeting an audio component. Audio components actually derive the audio parameter controller interface, so they already implement it. Outputs currently only feed to the audio engine, right? The audio render output and the OnFinished, for example. But in the future, there will be some method where outputs can actually feed back delegates into the gameplay system. So look forward to that. I don't know exactly when where that sits on our roadmap, but it is on our roadmap. Variables allow designers to cache data for reference in this and in future buffers. So variables are sort of just local to the MetaSound. And then sort of lastly, we have presets. And designing a MetaSound source graph for every sound source in a game is kind of impractical. It's also just a waste of time. Additionally, a new graph for every individual sound source is unscalable, especially if later on you need to change the graph behavior. So presets allow you to templatize your MetaSound source graphs. Okay, so you can think of your sort of graph design abstractly, and you'll be able to generate a bunch of presets out of it. So imagine, like, for example, a very simple the majority of sounds in a sort of your meat and potatoes audio experience are like randomized from a set of samples and randomized pitch and maybe volume and something like that, something along those lines. And so that could just be a preset that you then, put every single sort of simple random sound in. random sound source in different presets of that one graph. It could just be like the randomization graph, and then everything is sort of, then you're like, your footsteps use the randomization graph, or your, I don't know, your chipmunk chirps use the randomization graph. Anytime you sort of need some sort of basic randomization graph, you could use a preset, derive a preset from that one graph. And then later on, if you're like, oh, actually, I would like to also add, maybe some sort of enveloping and randomize the attack and release. That could something that you could add, and then it will just automatically propagate to all of your presets, which is very, very powerful, especially if you're midway in development and you want to change how a graph behaves, right? So in the future, we'll hopefully have a sort of special preset editor, which will make presets more user-friendly and even more scalable. Okay, this comes to part 2, understanding the DAG, or the direct acyclical graph. And to start out, you need to sort of think in buffers. This really helps a lot. So if you're not familiar, or maybe sort of somewhat familiar, right? In digital audio, we have this thing called sample rate, and we have this thing called bit depth. And sample rate is basically how many samples per second we are rendering or processing, and the bit depth is the sort of quality of each of those samples in terms of like the absolute number value. In other words, the resolution of each individual sample. What you find is that processing audio signals on an individual sample by sample basis tends to be an unoptimized way of doing things. It turns out that processing the signals in batches, in sort of small batches of samples, is a more optimized way of doing things. And it's just the way sort of like CPU architecture just sort of likes doing a bunch of operations all at once when possible. And so what you find is increasing the size of your batch, or what we call these batches, we call them buffers. Increasing the size of your buffer decreases the CPU costs. However, increasing the size of the buffer invokes a latency from the time the rendering begins and when the time that the sort of buffer is passed off to the user, right? So you can imagine these buffers like baking cookies, right? Like you bake cookies, but your oven is sort of optimized to like bake a certain amount of cookies. If you try to put too many cookies in at once, maybe it's too slow, or because there's more mass to be worked on, right? And so you're not getting the cookies fast enough. But if you go too small, then you're like, it's just sort of a waste of oven time, right? And so that's the balance. The balance is how large are your buffers versus how fast do you need the audio. But that's the way I think. When we're rendering audio, we're rendering in batches. And it's really just an array of samples. Like here you can see an array from index 0 to 479, which is essentially 480 slots, 480 samples. Okay, so this is where we want to think about buffer rate versus sample rate. So think about buffer rate as a subdivision of your sample rate, right? So in MetaSounds, different parameter types are processed at different rates as an optimization. So the default sample rate for MetaSounds is currently 48,000 hertz. This is something that could be adjustable, but right now this is sort of the way it is. And the buffer rate is currently 100 hertz. Okay, so this makes the audio parameter, the audio parameter that you bring in, that make outside of your wave player or whatever and goes into the audio output. That represents an array of 480 samples. And then triggers are actually very similar. Triggers are another sample accurate data value, but instead of an array of 480 elements, it's what we call a sparse array, and it just indicates, the array just tells us which samples in the buffer the trigger is being triggered on. But this is really important to sort of keep in mind, is that triggers are a data type. They're non-execution. We'll get into that later. Now, float, time, integer, string, etc. These value types are what we call buffer rate or control rate, and that means that there's only one updated value every buffer. So when you think of the LFO outputs, which are float outputs, that means it can only update 100 times per second. And if you know your Nyquist theory, then that means you don't want your waveform, your LFO frequency, to go above 50 hertz, right? Because then you'll get aliasing on your update. And so and 50 hertz is an audible frequency. So that's where you might be, if you need to update something that frequently, you might consider using an actual oscillator, an audio rate oscillator that spits out audio instead. Because sample rate, right, is very high precision. This is also why you might want to use a float envelope versus an audio envelope. The float envelope will only update its values at 100 times per second, and the audio output envelope can update its data 480. 48,000 times per second, right? So the envelope could, looping an AD envelope as an example that spits out audio is like having a triangle wave or a saw wave, right? That you can sort of move, adjust the timing of the attack and decay. So you can have very sharp spikes in your audio by using an audio envelope. So that's something to think about. And that's also something to think about on inputs. If something has an audio input, presumably it processes that input at sample rate. If it has a float input, it's only going to process that input at the buffer rate, and that value is going to persist across the entire buffer. And then this is something that I cannot overemphasize. Executions of blueprints are a sequential series of commands. But triggers are not a sequential series of commands. Triggers are specially marked samples in the data flow. Imagine the data on the graph is just like a bunch of river tributaries, all flowing outward into the output, and that's why you'll notice that the data can flow to many inputs from one output, but each input must only take from one output. And that's because we're not combining them there. So we have to have a special node for combining the data, right? So triggers are literally just an array of numbers that indicate which samples the triggers need to happen on. And so I want you to think about triggers as specially marked samples. It's like, imagine, adding some sort of, let's say you've got a creek, and you put like a rubber ducky in the creek, and that's your trigger. It's not a command. It's not an execution. It doesn't automatically execute each following subsequent thing. What it does is it just flows down the river with everything else. And because we're doing everything in batches, we're able to sort of capture the rubber ducks in the middle of one of our batches. That's sort of the power of triggers. That's why they're sample accurate, because we can specially mark samples in the middle of a buffer. And this will tell certain types of nodes that accept trigger inputs to start doing their thing, like rendering a wave file in the middle of a buffer instead of always having it be at the top of a buffer. All right, and then this real quick, sources versus patches. MetaSound sources are special MetaSound graphs which are derived from Soundbase and incorporate all of the Unreal Audio Engine's source parameters. You'll notice at the top of the MetaSound source, there's a little gear icon with source, and you click on that, and you'll actually get a details view of all of the Unreal Audio Engine source parameters. That's like, are there any? Does it belong to a sound class? Does it belong to? Or any audio modulation destinations ending, targeting that sound source? Does it render out to an audio bus or a particular submix? Does it send to multiple submixes? Does it apply, attenuation settings or whatever? All that stuff. Those are all relevant to sources, and only relevant to sources. And then also, that allows the regular sort of gameplay API for playing audio to also play MetaSounds sources, right? Whereas MetaSound patches are more like custom subgraphs, okay, or utility graphs that are designed by you to extend the library of MetaSound nodes and to sort of create custom libraries of MetaSound nodes. They don't have to process audio at all. They don't have to have triggers. They could be anything. They could just they could just be math. They could be math nodes, whatever. They could be all sorts of stuff. So it's just whatever you sort of special subgraph you want. And this just comes down to being efficient, right? Both MetaSound sources and MetaSound patches can be placed inside of a MetaSound graph, which is very powerful. That allows designers to build their MetaSounds out modularly, and more efficiently, right? So you can start, if you've got patterns that you want to reuse between different MetaSounds, you can create a little patch, or you can just reuse sources and then wrap them around larger MetaSounds, which is really powerful too. And then we have the set get and delayed gets. This is really something that catches people off guard a lot. And this is, again, it's about thinking in terms of buffers. So set sets the value of the variable for this current buffer. Get gets the value of the variable for this current buffer. And all the gets must be called downstream from the set, or you'll get like a recursive cycle. And this is an acyclical graph, right? We can't have recursion in this graph because that would just be an endless, because we're processing buffers, we're not executing commands. This is why we often use materials as a metaphor. There's no execution in materials. It's just a rendering graph, and that's what MetaSounds are. They're a rendering graph, and triggers are just a special type of data that allows us to specially mark samples in the middle of a buffer. That's all. And then delayed get gets the value of the variable for the previous buffer. And so this is really handy because you can recall the last value of the variable anywhere you want inside this buffer. And that includes, because trigger is a data type, that includes caching and recalling trigger data. And so that's why, for example, on the wave player, there's an option for on finished and on nearly finished. And on nearly finished basically spits out the trigger of what the finished buffer would look like one buffer early. And so as it's one buffer early, we can cache that and then get a delayed version that re-triggers the same wave player, and they will concatenate sample accurately, which is really powerful. This means that you can take something like a random set of samples, play them in your wave player, and have the wave player on the same wave player play the next one at the exact sample timing as it finishes the previous sample, right? Okay, so that's it. Again, my name was Dan Reynolds, Senior Technical Audio Designer at Epic Games. I'm embedded with the audio engine development team. My YouTube channel is here. Somehow you found it anyway. And there's my Twitter. If you want more stuff, more videos, I've got tons of Unreal audio related videos on my channel. And sometimes I do Unreal stuff on my Twitter, although my Twitter is kind of all over the place. Use at your own discretion. But there you go. There are some resources, and I hope this was helpful for beginners.